So, between us and lunch, we have another presentation. Now, this is a very interesting one. It's an overview of Traceroute, or a deep dive into Traceroute to understand how the internet works.
I don't think we could say it's a deep dive. We only have half an hour. I would need a few weeks. A lot of whiteboards.
You can
and
speak
patience.
fast. You can speak fast and make it work.
I'll try then to
So, Rauiri.
talk fast and not stand in your way for lunch.
Oh, yeah.
Hopefully. Oh, yes. Thank you. We can't always get what we want. So, perfect. Thank you. My name is Rauiri. I work for a company called Crusoe. Crusoe is in a small niche technology that nobody's heard about called AI. And it has the keywords like NeoCloud. It's a relatively new player in the game. They're building infrastructure. It's an interesting place. To steal Nina's line, this is my third DKNOG in a row, I think, with 3 different jobs, which starts nicely into my intro. Oh, these are old slides. No, I mean, it's an old deck. Can we change to the newer deck, please? I can talk. Yes. Thank you. The presentation I'm giving today, and this is actually perfect, it's not the presentation I started out writing. And that's not even the start of this story. I've had an unhealthy obsession with Traceroute for a very long time, probably 2 decades. The first time I use it, I was like, what is this? And then curiosity, I was like, how does this work? Quick question for the audience, actually. Hands up, who has used Traceroute before? Actually, let me ask a better question. Who hasn't used Traceroute before? Right, nobody. Okay. Hands up if you have ever worked with a customer and they've sent you a Traceroute. Now, keep your hands up if that Traceroute contained a smoking gun towards the issue you're debugging. Okay, I'm actually impressed. I thought that would be closer to 0. You're looking at your customers. The point I'm getting to here is Traceroute is fantastic. It's misunderstood. It's magic. It's fantastic at generating talks for NOGs. It's generated research papers. It's a wonderful tool. It is ubiquitous. It is everywhere. Everyone has used it. Thank you. It's not... I was joking yesterday saying that there is this trope in movies and TVs where you have these ink blots and you show them in front of somebody and they're like, oh, I see my parents fighting. I'm pretty sure I could print out a bunch of Traceroutes and show them to you and you'd be like, peering war. Misprogrammed fib. They're... yeah. So, what I was distracting myself from, I started this talk not as this presentation. I started with a simple linear, this is Traceroute, this is how you use it, this is how you read the output, done, linear. But as I started that, I realized there's a story to tell from the start. Where did it come from? And then I found it really hard to reason about it because it's not a linear, straightforward story. It's a complex, interdependent story with a tool that evolved as the network evolved. And then I realized that this presentation is actually 3 presentations in a trench coat. So we have network topology, we have Traceroute, and we have observability of the network. I did say I have an unhealthy obsession with Traceroute. Last year, I spent the year trying to build a basically distributed traceroute as a product. There's a bit more to it than that. I tried to build my own startup, and it was interesting. I learned a lot about Traceroute, and I learned a lot about what I didn't know about Traceroute. So hopefully I can bring something here today to you. So Traceroute appeared in the late 80s. From the README, I can see it's in about 89. I did something unusual. I started reading IETF meeting notes from the 80s, which are absolutely fascinating because some of them look like they're faxes. Bad scan in, but there's hints and there's talk about tools in about 87. So hands up. Who is younger than Traceroute? Yep, it's a pretty old tool. Another fascinating thing about the start, the origins, is you could consider it to be luck. So two people had just finished implementing raw sockets for ping, and that was the work that was needed to build Traceroute. It was built by Von Jacobson. He's an American researcher. I tried to track him down. I believe he is an adjunct professor in UCLA, but I couldn't quite find him. This first showed up in BSD 4.3 Reno. Thanks to Theo Lerad for pointing me in that direction. You can find the code online. It's pretty straightforward. It's about 300 or 400 lines of C. And what surprised me is that that version, that algorithm that was encapsulated in the C, is very similar to what we use today. So like I said, it was a suggestion to Von Jacobson, and he had previously a similar tool called TCP Trace, which I couldn't find the source for, but I understood this was more about tracking down nodes on a network than actual traceroute. So the first version, like I said, it's quite similar to what we have today. You have UDP probes. The key, the magic is that we use the TTL field in the header to figure out what path, what router is on the path. There's an interesting aside here where the TTL field originally was supposed to be seconds in the network. But because of competing implementations at the time on routing and IP software stacks, the version that used TTL as the hop count won. So we almost got a very different type of trace route. Because if that was based on seconds in the network, I think the buffer bloat people would be very unhappy. And I think that we wouldn't have all day long to run trace routes. This is back in 89. Networks were a different beast then. And this comes back to the fact that this is 3 presentations in a trench coat. And it is not a linear discussion. So we're going to be jumping forward and back a little bit. So as best as I can reason, late 80s, early 90s, the internet was growing rapidly. In some of the IETF notes, I noticed that NetNode was connected with an entire 56 kilobits, immense speed. I'm sorry, NordUnet, not NetNode. We didn't have many load balancing, multipathing on the internet at the time. It wasn't really needed. The first version, surprisingly, also had timing of the probes, but it is a little bit rough. It'll measure to about millisecond latency, which is fine. And this is another interesting aside. The first version was actually using ICMP probes instead of UDP probes. However, and stop me if you've never heard this before, there were some router control planes that weren't very powerful and weren't very happy with ICMP as the probe, so they moved to UDP, I believe, the night before they released the first version. This is from the current OpenB DWSD man page who has preserved some historical facts in there, and it's actually an interesting read if anyone wants to take the time. Because it also contains the first traceroute I could find, which is interesting because it is larger than I expected it to be. 18 hops. I believe the missing hops along the way are due to a bug in BSD, I want to say, where the devices were forwarding, taking a packet in with TTL1, decrementing to 0 and forwarding it, and it got dropped on the next hop. Oops. I'm so glad that all of these types of bugs no longer exist today. So, I mentioned the probes. Back in the 80s and 90s, and even early 2000s, the internet was hierarchical, but load balancing wasn't front and center. I'll make a lot of assumptions today around all of my examples. They're going to be based on roughly ECMP, cloud topology. That will be a 3-stage. And we will be doing and working on hashing, load sharing for layer 2, layer 3, and layer 4 tuples. So by that, I mean the IP, source test IP, source test port, and protocol will be used to make a forwarding decision. So I'll run through the algorithm for the first traceroute. What it did, so we send 3 packets out sequentially. We pick a random destination port and a random source port. Usually, you start at about 33434. You generate a packet that has a TTL of 1, destination port, source port set, protocol UDP, source test IP, and you send it into the network. Now, we can see that the source is the left top router. It generates 3 probes, 1, 2, 3. What happens is first packet goes on the wire, TTL gets decremented to 0, gets sent to the control plane. It generates an ICMP message, TTL expired, encapsulates the ingress packet into the ICMP message, puts it back in the wire, sends it back to the source. So now at the source, we know that this router has originated an ICMP TTL expired. We know the first hop in terms of TTL away from us. We go for the second probe. We increment the dest port by the TTL, by the probes sent. So we'll see the incrementing destination port, and that will be the only entropy in the packet that changes except for checksums. And because of hashing, we'll pick a different route and we'll send it out. And that way we can figure out roughly how many routers are a TTL away. We can measure the time, as I said, about millisecond resolution. So we can get a rough idea of the return time. However, one of the things that is missing is the wrong way to describe it, but one of the things I wish Traceroute could tell me is a return path. However, this is not possible for a lot of reasons, sadly. Anyway, so we only send 3 probes by default. You'll notice that we haven't got full coverage of what is 1 TTL away. It is worth noting, and it should keep in mind that what we're actually doing is not discovering all the hops. We're taking a statistically significant guess at how many hops are a TTL away. That sounds a bit difficult to reason and a bit abstract, but Traceroute won't tell you all the nodes on a given path. At the time, and the internet was relatively flat in terms of load sharing, this wasn't really a problem. However, in the last decade, we'll see that this is starting to become more common. Anyway, we move on to the next TTL, which is 2 away. You can see that we do the same algorithm. We're incrementing the destination port and changing the TTL for this run. And what's worth noting here is that you'll see the lighter color is the previous paths we've traversed. However, our first probe here packet number 1 on the diagram, it's taking a different path. But we will not record that router in the traceroute because it's not going to generate an ICMP for us. And same thing again. We go on to the next, we run the algorithm again, and we'll see that we're actually missing a whole bunch of information because of how hashing works. And we finish. And this brings me on to hashing, which comes under many names. I'm saying hashing. I probably should say load sharing, load balancing. It's the same thing here. So I mentioned back in the early days, the internet didn't really use hashing too much. There is balancing of traffic across prefixes with BGP policies. We just heard from the previous presenter about egress traffic engineering. So there's a lot of work getting done in the space, even today, for load sharing and balancing. When we come to having multiple paths on a router, we need to figure out a way to balance traffic and make a decision about what traffic should go to what path. So we can take the first real and easy way to do this would be per packet load balancing. And in the audience, could you put your hand up if you've ever had success in deploying per packet load balancing without breaking any applications? So we don't use the per packet anymore, thankfully. So we've evolved this a bit. We do flow hashing mostly today. Flow hashing is a shorthand for we use the layer 2 information, the layer 3 information, source test IP, and layer 4 and protocol. However, you can also use source IP, test IP, source prefix, test prefix. It's up to the operator to decide, but each of these different strategies will have a different effect on how Traceroute is run. I think it would be exhaustive to cover all of the use cases, and like I said, I'm standing between you and lunch, and I don't want you to hate me even more, so we won't cover an exhaustive list here. It's good to keep it in mind. And it's also a good segue into both observability and router architecture that I will try not to get into today. But if you see me around later, please ask me and I will talk for way too long about specifics here. It is a fascinating topic to figure out how does traffic get through a router, into the control plane, out of the control plane, what happens inside of this box of magic. It's one of my favorite games, which is where did the packet go? I mentioned we use different hashing strategies, and you noticed previously from the first traceroute, it was actually supposed to be ICMP probes. I'm glad it isn't actually, because of this simple example I used, which is the output from MTR. What you see here on the left is ICMP. It's run 5 times. That's it. That's just the only modification I've made to the command. And then for UDP, same thing, except I asked it to use UDP probes instead of ICMP. So we suddenly have extra hops appearing. It's well worth keeping in mind that there is ICMP as a probe type is very difficult to enumerate load balancing and multipath. I would suggest and urge to not use ICMP in this method, in this way for traceroutes. Try to go towards UDP or TCP. So, as I was saying at the start, this is an interdependent talk. When I started this, I thought it would be easy, and it is not. So the timeline of Traceroute is interesting, but is also dependent on how networks evolved. And as I was doing this, it was nice to see the way the internet has evolved over 30-something years of this history, and how Traceroute has changed. slowly over time. We can see the first one appeared in 87. What we call DKNOG Traceroute appeared about 90s. I mentioned MTR previously. That appeared actually way before I expected, in 1997. It had a little rebranding in 1998 from MATS Traceroute to Traceroute. TCP Traceroute appeared 2001. And what I find interesting is Paris showed up in 2006. I will talk a little bit more about Paris just a little bit. But it is really the first time we see a master's thesis done on Traceroute with publications behind it. And there's a very specific goal that they had in Paris. And then about a decade later, Dublin came along. These two last names are, if you couldn't guess, they're from the cities that the version was born in, invented in. And I thought we had nothing from 2015 to now. Max kindly nerd-sniped me just before I got on stage. There is more. So I'm going to move a little bit quicker now, sorry, because we have 10 minutes left. Quickly, DKNOG, roughly the same. Does parallel probing, adds AS lookup, which is really useful. Tightens up time resolution. MTR, I hope that you're all familiar with MTR. If you're not, I suggest you become familiar with MTR. By default, it uses ICMP probes. Not really a fan of, but what MTR does is actually quite smart. It runs your traceroute algorithm, but for every hop, it then runs a ping. So it can reason about packet loss because it keeps running like a liveliness detector. Or if you're unlucky like me, it runs a test on your control plane policing. So by that, I mean you're going to see loss where there's no real loss, which customers love and completely understand. And surprise, TCP Traceroute, would you guess, uses TCP. This is interesting because it does not change the entropy. And you know what they say, entropy is not what it used to be. Which means that when you run it, successful runs should go through the same path if you have a multi-path network. Paris. So Paris is a paper, it is published, you can read it. This is 20 years roughly after Traceroute came along. There's a bunch of topologies on that are now commonplace that it's hard to reason about from a default traceroute. Diamonds and loops, basically. And Paris was an attempt to figure out of the protocols, which fields in the headers are used for entropy. By entropy, I mean hashing decision. And they use those and manipulate just those fields and figure out what's my topology. And Dublin was more focused on NAT and ECMP environments. I will not talk about NAT today. I think we're all hopefully in the mindset that IPv6 will fix NAT. And NAT 6.6 doesn't exist. And it can't hurt you. Dublin is interesting. It builds on Paris work, but it brings two other things to the table. It has a library that's reusable, and it has a common exchange for traceroute information. And I believe the author of Dublin and Paris are talking about making this more of a thing where you can easily import traceroute into your app or build it in a library and have a common exchange format. I reached out to Antonio, the author of Dublin Traceroute, for some comments on it, and he pointed me in this direction. A quick mention about OpenBSD, recently revved their traceroute. No algorithm change, but it runs much faster. It does all the probing in parallel. So you can actually resolve a full traceroute in seconds versus tens of seconds. We'll do a quick trip down memory lane, and then I'll let you to lunch. Networks have changed, thankfully. Although I have noticed that we keep trying to reinvent ATM. We have OAM in Metro E. We have packet shredding. I mean, packet fragmenting in Ultra E, it seems like it'll never go away. We had a lot of software forwarding back then, networking duct tape, so tunnels, they've come along since the 90s. They changed the way Traceroute works. We'll cover it quickly. Today, unless you're doing DPTK, which is kernel bypass for faster routing, anything that's touching and forwarding a packet is probably going to do it in an ASIC. Overlays are everywhere. Like, I don't know if there's SPs out there that don't run MPLS, which is, again, ATM in a trench coat. VXLAN is now in the data center everywhere. GRE sticks everything together. We have IPv6, which is notable for a reason I will touch on in a moment. We have a more distributed internet. Things have changed rapidly. Here's a rough guess, and after talking to some people, this is how I'm kind of thinking of the timeline. IPv6 has been around longer than you think, and it's a shame its adoption isn't bigger. For a reason, again, I'll point in a second. We saw MPLS, late 90s was the first deployment. ASICs all over the place around the same time. We started to hash better around the Brocade Trident launch, Broadcom Trident, sorry, where we had a larger fib in a switch for cheaper and we could do routing. And that was when we also saw CLO appearing in the data center. And you can see, if you remember back to my previous slide about the origin of Traceroute, you'll see the two of them have a good mapping, that the networks change and there's a reaction in Traceroute. I will just skip to the end, sorry, and give you a summary and then let you ask me some awkward questions. This first line is directly from the first opening line in the Paris paper. Fatten Jacobson Traceroute is one of the most widely used measurement tools, and that is indisputable. There is a loose relationship between how the network's changed and how Traceroute has changed. And as I alluded to earlier, reading Traceroute can be like reading tea leaves. Some people are good at it. Some people get depressed and angry about it. They're all normal reactions. Something I'd like you to ponder is the fact that Windows Traceroute is the most historically correct version of Traceroute, and be horrified at that idea. An area I would love to work more on, and I tried to figure out and reason last year, is the asymmetry of the internet. Forward and reverse paths are never the same. It would be interesting actually to get the data from route views and figure out, can you make a reasonable guess about a symmetrical reverse path to a forward path? But like I said, ask me and I'll talk about this for ages. We currently can't really measure reverse paths. It is sad. And of that, I will just get to my queue questions, if you have any. I will thank you for your time. Sorry for eating into your lunch. No pun intended.
Okay, let's start from the queue.
Aaron Glenn, just a dude. As a longtime fan of Traceroute, I was wondering if you had any opinions on why it's been so ossified and not been developed over time.
Yes, I have opinions.
What was there one or two you wanted to share very quickly?
I'm not sure. Like I said, this journey of making this presentation, it led me down a different path I didn't expect. I was somewhat surprised that there is not more research in Traceroute. I'm also surprised that there's not more efforts to get reverse path into the mix. I know that Sako Yiti was working on an internet draft to do better timing, so you could actually reason the reverse path. That is still internet draft. Ben Carter Coxwright, I apologize if I butchered his name, the BGP Tools guy. He has a fantastic article called Splitting the Ping, and that actually reasons about the latency on a reverse path. But from ping's perspective, it wouldn't be hard to lift that into Traceroute. To answer, I'm actually not sure. Like, it would be wonderful to get more research and development in this area, but I'm biased as well, so. Does that answer your question? Okay.
I think if I can add something, I think it's people see it and think, "Ah, it's a simple tool. Why would I spend time working on it?" And yeah.
Henrik Ramselund from Security. I just want to ask if you know about RIPE Atlas probes,
Yes,
because they are awesome for doing debugging, and
yes,
you can like automate so much and do it from the command line even.
yes. There. Thank you for bringing it up, as well as the NL-NOG ring. You know what I'm talking about. Ask Job.
And there's also global ping as well. That's similar to RIPE Atlas. Yep.
Any other questions? Then one closing comment from me, if there isn't.
Go ahead.
We are actually hiring in Iceland if anyone wants to work in a data center. With, like I said, this new niche technology, AI. It's a pity that Joff isn't here from yesterday's morning's talk, because this data center is 80 megawatts of geothermal. Thank you.
Well, thank you.
And thank you.
So you go.
Thank you very much.
Thank you. Thank you. Thank you.